thought we'd learn how to sketch functions of the form y squared equals some function f of x. Because I love sketching functions, so why not do an entire video about it? We'll start off with a very simple function, f of x just equals x. We should know, of course, what this looks like. It's just going to be y equals x, which is, of course, this. Now, what does y squared equal f of x, or y squared equal x look like? Well, some of you will have seen it before. It looks like this, which is interesting for a few reasons. And I'll let you, if you want to, pause the video and think about all the interesting things about this. But I think there are three quite obvious interesting things. The first is that the graph is now curved. It used to be straight. It's now curved. That's interesting. Secondly, it doesn't exist over here. Like, there's just a completely blank area. The graph thinks about going there, and then it just doesn't and goes this way instead. So it doesn't exist over here. Now, that's kind of logical why it doesn't, right? It's logical because if you put in, say, x is minus 1, you get y squared equals x, which is just what this function is. So you get y squared equals minus 1, which can't happen because something squared is positive, minus 1 is negative, so that can't happen. So it's fairly obvious why it doesn't exist over here. And thirdly, the last thing I'll say is it's symmetrical now across the x-axis, which is interesting because it didn't used to be. So there's a few interesting things. And what I'm going to do is I'm going to plot a bunch of y equals f of x and then y squared equals f of x, and I want to know how many of these things that I've noticed hold every time and how many don't, and whether or not I can figure out the rules for, if you sketch this graph y equal f of x, what the rules are for sketching this one. So the aim every time, if I'm asked to sketch a graph like this, will be I'm just going to sketch this graph y equals, and then I'm going to use my rules to transfer it over and sketch the other one. But first I need to know what the rules are, and of course one example is not going to be enough to do that. So let's look at another one. Let's look at y f of x equals x squared. Now again, we should know what this graph looks like. It's this. What does y squared equal f of x look like? Well, it looks like this, which is interesting, again, for a few reasons. Firstly, it's not curved. It used to be curved, and now it's not. So it's gone the opposite way of what it did before. Also, it exists everywhere, which the other one didn't. It's still symmetrical around the x-axis, which is good. It's also symmetrical about the y, but I know that can't be a rule because the previous one wasn't. To describe exactly why this graph looks like this, quite interesting. You can just say, okay, well, f of x equals x squared, so y squared equals x squared. Root both sides, of course. If you take a square root, you need a plus or minus, of course. And now we're literally just saying you want to draw the graph y equals plus x, or y equals minus x. Of course, y equals plus x is this line, y equals minus x is this line. So that's how we draw that. Let's look at another one, a very similar function here, x squared plus 1. Now again, we should know what this looks like. It looks like that. Is y squared equal f of x? Well, if this function is just the previous one moved up one place, does that apply to this graph here? Are we just going to move up the graph we just saw by one place? Well, we're not, actually. Graph transformations don't work if you have a y squared, apparently. The graph looks like this. And there's a few interesting things to note here. We still have symmetry around the x-axis. And at this point, I think I'll just prove why we have that every time. The reason we do is if we take the square root of both sides here to get y equals plus or minus root f of x. Now again, as we just saw, I can say that means we're drawing two graphs. We're drawing the graph y equals plus root f of x and y equals minus root f of x. But root f of x is just some other function where you've just put a root at the end. Imagine it as like a function machine where you're asked to square first, then add 1, and then the last step is to square root. So this is just some other function. I'll call it g of x. And this is the minus g of x, of course. But from graph transformations, you know that minus g of x is just g of x flipped in the x-axis. So this is literally just telling you to draw some function g of x, which could be this, and then flip it in the x-axis and draw that too. So this is always going to be symmetrical in the x-axis because it's literally just asking you to draw a function, flip it over, and draw that one too. So that's kind of cool. So we have one rule that we know for sure. Graphs of this form are always symmetrical in the x-axis. That's cool to know and good. Now, the other thing that's interesting about this graph is there's a corridor, a horizontal corridor here that's missing. So let's explain why that's missing there. Well, here, like y is 0.5, right? So if I put in y as 0.5 and square it, I'll get 0.25. And then we look at this carefully and we think, well, actually, x squared is either positive or 0. Right? Because when you square a number, it's either positive, or if you take 0, it's 0. And then when you add 1, you're never going to get to here. Like this number here is always bigger than 1, which we can see here. It's always bigger than 1. So there can't be any, we just can't put in a function, we just won't get any output if we put in y as anything less than that, until we get down to minus 1, because of course, The whole symmetry we described earlier means that we can do that, because if we draw this, then we draw this too, as we just described. So that's kind of interesting. Let's do some more examples. What if we shift it down? So this is the first rule we actually know. Symmetrically in the x-axis, everything else is still a bit mysterious to us. But what happens if you do, again, a similar function, but we'll move it down this time? What does y squared equal this time, or look like this time? It looks like this, which is very similar to the graph we just saw. It's just now got a missing corridor in sort of vertically. And let's think about why this corridor is missing here. Well, if you put in y is 0 into this, y squared is x squared minus 1 here. And if we put in x is 0, if we're here, we put in x is 0, we get y squared equals 0 squared minus 1, which is minus 1. And you can't do this across the real numbers, as we said before. So there's not going to be a value for this. And likewise for 0.5, 0.5 squared is 0.25, minus 1 is a negative, so we can't do that either. It's only when we get across to 1 that we can actually do 1 squared minus 1 is 0, and then y squared would be 0 as well. And then, of course, this is the symmetry across the x-axis, and the same thing happens when you put in the negatives, because negatives square to positives. So that's kind of cool. So we're missing this corridor, and we can extend that idea to say, okay, well, if you have the original graph, and any area in that graph is negative, then that implies a missing corridor in your y squared graph, right? Because any of these inputs here, like 0.5, gave you a negative f of x, but you can't do y squared equals a negative number. So all of these values here, all of these values between 0 and between 1 and minus 1 that give you a negative f of x output, they're all going to be missing because you can't have y squared equals negative. Right? So this is our second rule, is that if you plot the original graph, y equals the function, any area that's below the x-axis is just going to vanish. So that's quite cool as well. So we have two rules now. Let's look at this graph. So this is a cubic, has roots of minus 1, 0, and 1. Cool. Looks a bit like this. So let's make some quick predictions about this. The graph is negative between 0 and 1. So when I'm sketching this graph here, I think the graph will vanish in the corridor between 0 and 1. I also think it will vanish between minus 1 and negative infinity, if that's a thing I can say. I think it's going to vanish all the way over here. I think it's going to vanish here. Now here, we've discussed already this rule here. If the graph does exist, it's going to be symmetrical in the x-axis. So I'm predicting some kind of egg shape here, because this graph will kind of will reflect like this. And here, this line will also, or curve here, will also reflect to make a shape a bit like this here. And this section and this section will disappear. And yeah, we end up with this kind of shape here, because that's this bit reflected. This section completely disappears. That corridor disappears. This corridor disappears. And this section also reflects in the x-axis like so. The only question that remains is when we look at this graph, this curve has kind of become more bulbous, right? Like it's gotten bigger like this. And this curve, which used to, it looks kind of convex here, it looks more concave now. So there's not only these missing parts and this reflection, there's one more thing going on about exactly how this graph changes. Like in what way it becomes curved, maybe. That's the last thing we need to investigate. And to do that, actually the easiest thing to do is look at the very first example we did, which is f of x equals x, which is just this line here. And now think about y squared equals f of x. Now we know it's not going to exist over here, because the graph is below the x-axis over here, so it's not going to exist there. We know there's going to be symmetry, so it's going to go down here and come back down here. Now, we've already seen in the first bit it looked like this. Now, why does it look like that? Well, it's because when you square root both sides, think about what the square root does. Now, f of x is the output, of course. F of x is the y-axis, essentially. It's the output. When you take an output like 3 and you square root it, it gets smaller, right? So the output, so when you put input 3 in the very simple function x equals x, when you input 3, you get the output of 3. But when you square root that, you input 3, you square root the output, you get to like 1.7. So the graph flattens itself down. Likewise for 4, 4 used to go to 4, but the square root of 4 is now 2, so it flattens down to 2. So this entire graph will flatten down to look a bit more like a log graph and flatten or squash down to look like this curve here. Except for one particular place, which is in between 0 and 1, because the square root function doesn't always flatten or make numbers smaller. It does most of the time, But there are some numbers that when you square root them, they actually get a little bit bigger. So the square root of 0.25, the square root of a quarter, is a half. That number gets bigger when you square root it. And likewise, 0.01 square roots to 0.1. That number gets 10 times bigger when you square root it. So when you have an output between 0 and 1, like this one, 0.5, that's going to square root and become bigger. And so between 0 and 1, if you have any part of the graph that's between 0 and 1, it's actually going to raise itself up. Not flatten down, it's going to raise up. Because when you root numbers between 0 and 1, they actually get bigger. So this graph flattens itself down as soon as the output is above 1, and raises itself up when it's below 1 and above 0. And so it's going to, those two things combine to give it this very satisfying curve here. You can see why it's so vertical at the start, because very small numbers square root to something significantly bigger. So it sort of stretches up here and then flattens down afterwards. And that's the last key idea that we need to understand for these. So okay, we'll put this all together. Of course, this graph is very similar to what we just saw. We just shifted up one place. But of course, what does y squared look like? Well, it doesn't exist beyond -1. That's the key first thing we learned here. It is symmetrical in the x-axis, so any parts that do exist are going to be reflected. And finally, any output above 1 is going to be flattened down, and any output below 1 is going to be raised up. So we're going to have that same raise up there, flatten down afterwards. Symmetry here doesn't exist over there, and we'll end up with this shape here. I'll just do a few more of these because they're really fun. Let's be more ambitious. F of x equals sine of x then. We should know what this looks like off the top of my head. I've done this in radians because I couldn't be bothered to make the graph in degrees. It just would have taken 30 seconds more of my life and I couldn't be bothered. So anyway, f of x is below 0 between pi and 2 pi. So it doesn't exist in this corridor here. This graph, I mean, won't exist in this corridor here. It won't exist here onwards. It won't exist between here and here. It won't exist between here and here. The parts where it does exist will be reflected, so they'll make sort of a circular shape. And also, because all of the outputs are between 0 and 1, this graph will be entirely pushed up a little bit and become more circular. So I'm expecting gaps between these two values here, gaps, 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 and also these parts raised up and reflected to make sort of a bunch of disjointed circles is what I'm thinking about. And yep, perfect, the graph agrees with me. A bunch of disjointed circles. These parts raised up because the outputs are between 0 and 1. Roots of those things get bigger. Symmetry in the x-axis, so reflected around, and these parts just don't exist. Cool. Another one, I don't expect you to know what this graph looks like, so I've given it for you. But okay, so we've got. Let's think about this. We've got a negative output between -1 and 2. It looks like there's an asymptote at 2. So the graph won't exist. This graph won't exist between -1 and 2. Here on this section, the outputs are between 0 and 1, so they'll be raised up. So they'll get a bit taller and also reflected in the x-axis. So we're expecting some kind of like pencil shape here. And here, the outputs are bigger than 1, aren't they? It looks like there's an asymptote of 1 here as well. The outputs are bigger, so they'll be squashed down. So this whole section will be squashed down a bit and also reflected in the x-axis to make another thing that has an asymptote at -1 this time. So expecting this kind of thing does look like this. Really cool. One more to do, being a bit ambitious here. Let's look at this graph here. Very interesting graph. Looks like this, which is really cool. I like graphs that look like this. You don't really see them much even at A-level, but they are really cool. Let's look at this then. So we've got an asymptote looks like at 2, and it also looks like we've got an asymptote at 3, which are no coincidence here. Now the original graph is negative below, looks like 1 and 2. So there's going to be a short, small corridor between 1 and 2 where this graph doesn't exist. Also, same between 3 and 4, there'll be a small corridor where this graph doesn't exist because it's below the axis here. Now these outputs are below 1. Now this looks like 1 here. 1, 2, 3, 4, 5. So these things will be raised up a little bit, become a little bit more rounded and also reflected, just like the previous one. So we'll get two sort of pencil shapes here and also here. Same thing happening here. And then this section of the graph, now this section has big outputs, right? So this section is going to be flattened down. This looks like it's at 9. So it's going to be flattened down to 3, and likewise all the other bits. So this will reach down further and flattened down to 3 as its new minimum, but also reflected. So there'll be another shape coming upwards from below. And we should end up with something that looks a bit like that, which is really cool. And I really enjoy sketching graphs like this. They'll come up in interviews often as well if you're doing university interviews for maths. So yeah, it's well worth having this in your wheelhouse, I think. Anyway, thank you for watching, and I'll see you next time.